Rainy. Rainy, I think.
I looked this morning early, about 7:30 or so, and had about 3 o'clock rain. I don't know if that's still holding around.
You know, we have 3 days off in a row now.
Why?
Next Wednesday, Thursday, Friday, because of mini semester, that's their finals.
Wait. Next Wednesday?
Next Wednesday, Thursday, and Friday, everyone that's not in the mini semester has off.
But we have Monday class.
Yes. And then the Monday after that, the 28th, we don't have class because of Juneteenth, which they just made official.
Yeah, I saw that.
Yeah, so we have 3 days off in a row.
Insane.
Yeah.
I don't know who came up with that one, because you realize we have so much material we have to cover.
That's what I'm saying.
Okay. I didn't make those calls, I'm glad. And we will pull up. By the way, we're in the 4th week, aren't we? Or 5th? The 4th week.
That's a good question. Well, it's fourth wins, so fourth week.
I'm guessing, but the first week we didn't have one. We started on Wednesday.
Yeah, that's kind of halfway.
All right, so why don't we do this? For the 3 days that we don't meet when we should meet. So the Monday, how about Monday, we vote on when you want your first test. Let me give you a piece of advice here, okay? I don't care, but I mean, I'll let you guys figure it out, and we'll put up the top 2 or 3 candidates days, and you'll vote in class with your hands, and I'll count. And that way there's no kind of, I guess, question about the legalism or how valid it was. Long story short, people don't trust online voting. I found this out. Anything that has to do with them not seeing how others vote, you can forget it. They don't believe it. So anyway, here's the deal. We have done chapters 6, 7, and 8, or we're getting done with 8. We'll be done with 8 today, probably. Chapter 9 is EMC. This is, and it's a good, I make it very applicable for the knowledge base that you have, how it applies. Now, EMC is electromagnetic compatibility and interaction. That's really how components look at high frequencies, what happens to circuitry when it becomes susceptible to interference, and how do you mitigate or get rid of that interference. It's a good part of the course because it's practical, and if you're designing stuff, you're going to want to know some of these things. Usually, I mean, honestly, when I was in physics, they taught you a lot of theory, but how to actually do something, things to look out for and build it, you don't get that. In engineering, we're supposed to be very aware of the fact that you're going to be designing and creating things. You got to market. So any problems, at least that I've faced and ways I've solved them, I'm going to try to express and tell you about. Now, that said, I would recommend you get the test probably before the 2nd week of July, probably because isn't it July 30th? It's the last day of class, I think.
Yeah.
All right, so at least by the 2nd week, 1st week, but any time after our 3 days of holiday. All right. Now, I know, I've had students that whenever they get a day off, oh, great, we got too many work days anyway. Don't think of it that way. You're paying for this, all right? And the less time, the more you're going to have to learn in less time, which means it's sort of shoehorned in there. So first thing, questions about the homework. I got somebody, Hunter, you emailed me about a problem, right? 7, was it you?
Yeah.
7.2.2 or 7.2.3, one of the two.
Yeah, that's the same, you just changed the units. I think I was typing it in wrong. You can do it, I could hit 7.2.4, but not 3, and I was just changing the exact same thing.
Who asked me about, Jacob, you asked me about this. Did you show him how to do it?
Yeah,
Huh? Yeah.
I am not.
All right, I saw you guys up in front. If you know how to do it, I won't mess with it, but 7.2.2 or 3 do you mean?
You gotta solve 7.2.2.
Yeah.
All right, tell me what 7.2.2 is.
Lossless quarter wave monopole, 100 volts, 300 megahertz. Source impedance is 50 ohms. and it wants the average rate.
That's VRMS or VP?
It didn't say, right?
This is the peak, yeah, it doesn't say so.
It's peak, okay. And they got what, RS of what? 50?
50.
All right,
It wants the average power radiated
okay.
and the magnitude of the electric field at 90 degrees.
All right, we need the current for that or the total power radiated, either one. So this is a 100-volt source. This is a 50 ohm thing. And that's a quarter wave monopole, right? So what we're going to do to get the quarter wave monopole impedance is we get that half wave dipole and divide it by 2. Do you all follow me on that? So we get the dipole impedance divided by 2 because we're radiating half as much power with the same current means the radiation resistance is half. So that means Zn to the antenna would be equal to, well, for an exact half wave, and that's what I think they assume, it's 73.2 plus J 42.5, divide that by 2 because it's a monopole. Does everybody agree with that? All right, so that's the input impedance, whatever that is. It's what? 36.4.
36.6.
Yeah, plus J 21.25. All right. Y'all with me? So that means the input for the antenna is 36.6 plus J 21.25 ohms. That's fine. Now the next thing we're going to do is find the current that's actually flowing into the antenna. Are you with me? Everybody understand what I'm doing here? Why I'm doing it, right? So to get that current, this will be a peak current. I peak will be, and if it's flowing there, will be 100 volts. It's the voltage source divided by the sum of the impedances of 50 plus, and this would be the antenna impedance, 36.6 plus J 21.25. Now, give me that in terms of a magnitude and an angle. I sent you this solution, Jacob. I don't remember it though.
1.12 at an angle of negative 13.8.
13.8?
Yeah.
All right, you don't need that angle at all. All right, now, once we have that current, there's a couple ways to get it. We can go to the equations of the half-wave dipole to get the E field, all right? Or we can just get the total power radiated, then get the E field from that. Get the total power radiated by taking 1/2 I squared times R, the radiation resistance of the antenna. Do you all follow me on that? All right, so I'm going to do it that way because it gives a little more information. So when I take a look at P rad, right, the radiation would, P radiated would be 1/2 the magnitude of the current squared times the radiation resistance. I'm putting it down so you'll have that for record when I start filling in. So this is going to be 1/2 magnitude of 1.12 squared. And the radiation resistance of the antenna is this. It's the real part of the input impedance to that antenna, which is 36.6 ohms. So give that to me.
23.
Say again?
23.
23 watts. Everybody agree with that? Did you all get this too? Did you guys get it? Did you do this? No. No. Did you do it? Not you. It's Freddie. Yeah. All right. I mean, if you have questions, be sure to ask. I don't want anybody left out in the dark on how to do this. It's straightforward. So you got that. Now, after that, I'm going to use the way I do this with finding the power density at the point of observation. And then after the power density, I'm going to get the E field. You all follow me on that? So for that, to get the average power density, this is the way I do it. I'm going to take the total radiated power over 4 pi R squared. Now that would be as if it was an isotropic radiator, right? I haven't determined what R is yet. I haven't stated it. Now, after that, we're going to multiply it by the gain, and please be attentive here. Remember, this is a quarter wave monopole. That means it radiates over half the space of a half-wave dipole with the same characteristic current. Do y'all follow me? Which means the gain is double. Do y'all hear me on that? I can do this a different way. I could figure out the current and prove this to you from the E field, but I want to make sure you know this. So now I on purpose take 2, because it is a monopole, times the gain of a half-wave dipole, which would be 1.64. And I'm going to put in the angles here for everybody's sake. Cosine of pi over 2, cosine of theta. And this thing is divided by sine of theta. I told you it looks a lot like a sine curve, didn't I? And it's that squared. Remember, there's a square there. But the nice thing is, the largest this angle can, or this function that theta can be, is 1, just like the sine. Remember that. It's very close to sine squared, very close. Now we take that, and that's it. So the angle was what, 90, right? All right, now the angle is 90, which means that is 1. So now I put in the values. The P radiated was 23 watts. Do this with me if you haven't. Over 4 pi, what's the range R? 100? So it's over 100 squared. And now times 1.64. And this will be 1. So I just leave it alone. And that's the power density in watts per meter squared. You can tell me what that number is just for everybody's sake. We got this on camera, so.
4, 5 squared.
I didn't ask this, the problem doesn't ask this, but it's nice to know how to get this.
I got 3 times 10 to the -4.
Anybody else?
Same.
All right, so it's 3 times 10 to the -4 watts per meter squared. Now I know that's a power density, right? Immediately, if I want E or H, I just go to my go-to equations, which are 1/2 times magnitude of the E field. They asked for E, right? Over eta naught, and eta naught is 120 pi ohms, or about 377 ohms in free space. That's equal to this. 3 times 10 to the -4th. And therefore, to get E in magnitude, that's the only thing you care about really in the real world, it's going to be simply 2 times eta naught times 3 times 10 to the -4th, and it will be the square root. You can tell me what that is. I think the book's right, because we checked with you, I know that. At night, when I finally get down to emails, I mean your emails, what I'll do is pop up MathCAD and just do the problem real quick. And this is a piece of advice. If you want something that'll get you through these kind of problems super fast, learn how to use MathCAD, PCD. It's much better, in my opinion, than Octave or anything like that, or MATLAB, because what you see is what you get. You got, cryptic formulas with Greek letters and all that. It'll show it, and you can manipulate. So what'd you get?
I got 0.47. Yeah, I got 0.475.
Is that the answer? Huh?
Now you're talking about for 7.22?
Yeah, for the
E field.
E field. What is it, 74?
What is it? I mean, I know it works because we did it.
Yeah, it's about
I sent the solution to you. I can forward it there, but I know it works. I know the answer is right. So somehow, is this right, Jacob?
Yeah, that's the way I would it.
But I don't think that's right.
Oh, you know what? We forgot the 2 here. That's the problem. Multiply that by 2. So this is going to be 6. Yeah. It should have been 6 times 2 times, 23 times 2 times 1.64. That's on me. It should be,
Here we go.
is that right?
Yeah, that's right.
My bad. So this is really 6 here. And this is what was the answer?
0.67 volts per meter.
Volts per meter?
Yes, sir.
That's a pretty big electric field, huh? What? I'm sorry. I'm just trying to level. When you get volts per meter from an antenna, you're either very close or they're putting out a lot of power. At 100 meters, you're pretty close. If you get a couple miles away, there's no way you're going to get any field like that. Unless you got a super power, you're radiating a lot of power with high gain. The volts per meter makes me a little nervous if I'm in the real world and I start. I'm walking into like a range, a microwave range where I might get fried. I want to tell you one thing too. I don't know enough about this stuff to really comment, but I know about the MRI research, nuclear magnetic resonance stuff that they have out there. And I've been hearing about this EMF fields affecting health. I'm into being healthy. So it's electromagnetic fields. And they can affect you with the Wi-Fi. They're worried about 5G. 5G is the same thing as 4G, just the inner architecture is a little different. It's not that they've got this frequency of, 5. They don't have some new frequencies and all this stuff. Anyway, I'm listening to these 2 doctors talking about intelligent people and talking about EMFs affecting health. So I'm thinking to myself, I want to just tell you this because this is something that's actually useful for you to be aware of. Your skin and everything, it has a fairly high conductivity. It does. Water, I mean, you're made of salt, right? Salt itself, anything moist and salty, things don't penetrate well. Now, the MRI guys have to do a whole lot of stuff because they have very low frequency magnetic fields that they first embed in the human being, and then they turn them off. They shift them 90 degrees, and it causes a big transient. And whenever there's a time-varying magnetic field, there's a time-varying E field. And so they get this stuff down in you, and then you might say, and they change it, and they worry about thermal heating. That's the only thing. I've talked to Tom Denny over there. We've got a world-class group over there. They do research with 6 Tesla MRIs, normal. And has anybody here had an MRI? One? You've had 3?
Oh, no, I was raising my hand, had 1.
All right, I've had about 4 or 5. I've had it on my knees, I've had it on my head, maybe my shoulder. Anyway, I've had plenty. All right, you don't know you're in a tube. I mean, you can't feel the magnetic. There's nothing about that in any way, shape, or form tells me I'm being affected by electromagnetic energy, even though it slightly elevates temperature, very slightly. When you want to feel the effects of photons of electromagnetic energy, go outside in the sun. You'll feel it. Do you feel it in your belly, in the center, or in your heart? No, you feel it on the skin. That's where it can affect you. All right? It can affect you deep down. Now, it can affect your eyes. You can get cataracts. You know what welder spots are? Anybody? If you're a welder and you don't wear a mask, the UV radiation will destroy your retina. Now that's a little different. That isn't just thermal heating. That causes a shear because the electric field is so strong. Really, it's a long story on this one, but it causes destruction of tissue that way. In order to have that kind of destruction, you have to have very high frequency UV light or higher X-rays and stuff like that. So I'm listening to these guys and talking about electromagnetic fields are affecting all these people's health. Now, it is true if you get near a large power substation where they've got a whole lot of current, maybe 70, 100,000 volts. I've been told this. I've never done this. You can take a neon light. I mean, not neon, sorry. And a fluorescent light and walk up there at night if it's pitch black, and you'll see it start glowing. Right? Kind of makes me worried because, see, that's near field energy, but now you got a conducting path. Did I tell you the story about the guy stealing power for the power company with the air transformer out west? It's Friday, I might as well just do it. So out west years ago, there was a guy, and they caught him. He had this huge farm, And, you know, the power company has what's called eminent domain. They can run power lines. They have to pay you something if they're going to cut up your crops or whatever, but they can run power lines through you. So this guy's got these things with power lines, high voltage power lines up there. Also has huge trees. So the power company starts noticing they've got this huge loss in power around this guy's. Do you know this stuff, by the way? Anybody? All right, and you can imagine what's going to happen. And this guy's an electrical engineer, I think. He's either that or he's close, whatever he is. Anyway, so they sent this guy out to investigate there. You know, when you think about losses, normally what they do is they think about eddy currents induced in the ground. They think I've got a lot of iron in the ground. That's where the losses are. But there's really, when they see this tree, and it's kind of hiding the power lines. That's kind of maybe kind of wacky. Trees know the guy had built a transformer. So here's the high voltage line, one phase, right? And what he did, do you know what a Rogowski coil is? Anybody? All right, I could check. He's got a coil of wire, all right, around this thing. The Rogowski coils, I'll just tell you this, because it's worth knowing. Here's the power line with a lot of current. Don't worry about the voltage, a lot of current, all right? Now there's a magnetic field that swirls, all right? Like this. Y'all with me?
Mm-hmm.
All right, now, if you put a donut around here, go around this way. Y'all follow me? So it goes around the outside, and then you wrap that donut with a lot of wire. That magnetic field goes through the center of that thing. Follow me on that?
Mm-hmm.
And there's a flux through each one of those turns. This current is time varying. So you got this huge bunch of coils. It's called a Rogowski coil, like this. And they're very close to this power line. That means the magnetic field's very large. And this is, you know, thousands of amps. This is a major power artery. So they got time varying magnetic field. So this guy knows what he's doing. So he takes it up. That's where it's hidden well, by the way. This guy's clever. Green and everything, from what I remember. You should look this up. Now you got a lot of voltage, right? I mean, you got the time varying change of the magnetic field is going to be the voltage. Comes down there, and I think he rectifies it through a full wave rectifier. Then he takes that and chops it up into 60 hertz, whatever, for a 240 line, I think it was, for his power and stuff like this. And this guy's been, you know, milking the power company for free, probably millions of dollars with power. So they caught him. Boy, did he violate some laws. Now, it's on the books with the FCC. Matt Company thought he could get away with it. Anything that's transmitted over the airwaves is yours. They can't, you know, if you decode Sirius XM or anything that's broadcast that's normally a paid for thing. You know what Sirius XM is? It's paid for radio. If you've got some way to crack that, they can't get you legally. All right, I guess maybe they can nowadays. All right, anything broadcast is free. They can't charge you for that. But here's the thing, that's near field energy. That's where he didn't pay attention to the fine print on the FCC laws. And you can't cull or pull near field energy out of the air for your own stuff, all right? That's illegal. So anyway, that guy got a huge amount of trouble. FCC laws are violated, fair trade laws, probably state laws with theft. Anyway, I don't know how long his jail term was, but I read about that, and he's a clever guy. I got to give him that. All right, but you know, don't ever try to do something sneaky when you know deep down it's right. So getting back to my EMF stuff, that's EMF. That's near field. He's putting, obviously, it's a lot of power in there, right? Now that might thermally heat you up enough to cause problems. But I'm listening to these guys, and they're absolutely like throwing down. Like, this stuff is going to kill you and all this. So I want to see some studies. They've got one physicist at the University of Washington they cite who's got some evidence that I guess sticking a cell phone transmitter or something near rats or something, they actually develop some sort of, they have more chance to develop cancer. They literally paste this thing up. It's like, yeah, sure. If you put that on your head, it's going to heat it up. It's usually the heating or that there's an attractive force for some ions. But anytime you have just transmitted electromagnetic energy out there, incident on you, not near field, your skin is about as deep as it goes. Y'all with me on that? So when you get near microwave energy, there are weapons that actually are used. They have human deterrence. If they're trying to do dispersion of a crowd, they develop this where they can put a this is an emergency. They won't use this normally. The media finds out about the ghost there. But if they have to get a crowd out of there for something, say there's a nuclear weapon going to go up, then they have microwave stuff, and it will burn your skin. You'll feel it. It won't really, but extremely uncomfortable, and you'll see people scatter. You can look this up. It's microwave energy for crowd dispersal. But all this crap I'm reading, and it's not just them, others, I'm thinking they don't know what they're talking about. There may be an effect, but it's not due to the stuff inside. Maybe it's causing some sort of ion particles in the air nearby or something, but it's surely not what they're coming up with. And I don't know if you've ever been around people that are just, they believe in pseudoscience. I mean, they know something is true. They just know it. And you know what dowsing rods are? Find water.
Yeah.
Okay. I'd love to see the science behind it. Just anything. I mean, I can't even get a level answer. Oh, it just works. Okay. If it works, it isn't for the reasons I've heard. Okay, back to now the full circle. So that's my Friday story. I don't know if you want to hear any more of these, but I try to share things that I think are at least relevant to the topics. And believe me, there's some wacko stuff that I can tell you, especially things that are unexpected. And wait till we get to some of the EMC stuff. I got stories about railguns, scary. All right, so now we're talking about the full circuit. I've given you a few more problems about arrays, all right? Arrays magnify things. They're our friends. If we want a much bigger power density / electric field at a point, we use that. If we want a much higher gain, we use arrays. But antenna arrays have some downsides. There's side lobes and stuff like this. Overall, they're our friend. It's a way to get more gain. So now we talk about the full circuit. So this is the complete circuit of an antenna. You had Friese, and remember with Friese, you had this. You had antenna 1, right, the transmitter. And this transmitting antenna had some P radiated into it, or P transmitted, I think is what Whitworth uses in the book. It has some gain of the transmitter, and if you come out a certain distance R, then you found out that this is the gain of the receiver. I hope you don't mind me just putting a subscript R there. I use gain, not directivity, because it's more inclusive. There is an assumption that is not stated. It assumes, when we talk about P received here, I'll put the equation down. P received, right, is equal to P transmitted, then it's times lambda over 4 pi R, right? And this whole thing squared, then it's gain of transmitter, gain of receiver. That's the Friese equation, right? All right. That P received is not the power that is actually received. I mean, it is and it isn't. That's the maximum possible power that can be received theoretically. You all hear me on this. So that's the theoretical maximum. Even that isn't the amount of power that we can use if it's matched. So here, what happens is, normally they assume that they have some Z load, and this Z load has a value that is the conjugate of the antenna impedance. That star up there means conjugation, and conjugation, simply put, flips the sign and the angle. For instance, if the antenna impedance was 100 ohms at 45 degrees, the conjugate of 100 ohms at 45 degrees would be 100 at minus 45. Y'all with me? Now, or you could say if it was 50 plus J50, the conjugate of that would be 50 minus J50. Y'all with me on this? Conjugation is something you have to know. So if that's the case, that's how they look at that. Now, what I'm gonna do is this, and try to understand this. That circuit right there shows an antenna that's hooked up to a load. Normally, the way we think about the antenna when it's receiving power is this. There's some voltage here, but it's an open circuit voltage. We're going to determine that. Are you with me? Now, the antenna itself has some internal R antenna, and then it has some reactance. It doesn't have to be in real, a positive. It can be imagined, or it can be negative J. So it's plus JX of the antenna. Here's the output of the antenna. And now the load will have the real part, R antenna, but the imaginary part will be minus JX antenna.
Is this just for receiving antenna?
Yeah. And this is the way you view the circuit. Now, I'm going to get to something in a second. That VOC is going to be a peak value. All right. Here, there's going to be a current. I just want to mention that current becomes essential. When you look at this, you can call it I load. Remember, we talk about P receive, this is the circuit should come to mind. Now, if you take a look, if you want to calculate this current, IL, right here, you would take VOC and divide it by what? The sum of these two. You see how the imaginary components get rid of themselves? You would only have two RANT, right? So let's just do this. So now I have I in the load is equal to VOC divided by 2. And you can call this RRAD because it is the radiation resistance of the antenna. So RRAD is R antenna. That's I. You with me? Now, what is power? Well, power, all right, in general, this is the power, P received. So it'd be P received. That's the total power being dissipated in the circuit. Go with me? What is that? That's going to be 1/2, right? I squared, which is going to be, you can do this way, I squared, which is going to be VOC over 2 RRAD, right? Squared times RRAD. Actually times 2 RRAD. Right. Because the power is dissipated through both resistors, right? Are you with me, everyone?
Is
Yeah.
the RRAD and the load, are they always the same?
When you're calculating P received, the assumption this works is that this load is the conjugate of the antenna impedance. If it's not, the reason the conjugate, then you get rid of the imaginary parts. All right, then you have a peak amount of current possibly delivered, or peak power delivered. Now there's a theorem, you remember in circuits you had to do this? What is the impedance of a load if you want a couple of maximum amount of power from a source voltage and a source impedance in series with it? It's when the load impedance is the conjugate of the source impedance, right? Typically, Irwin starts with resistance. He said you got RS, what do you need to make RL for peak power coupling? And it's equal, all right? Well, in general, a more general way to say this, it's conjugate of the impedance of the source. Now, when you do this, if you look at what happens here, one of these One of these RRADs cancels, right? I mean, 2 RRADs. So now I have this, I still have V squared, but it's equal to V open circuit squared. This is the equation you write down over 4 RRAD. This is in your book. If somebody can tell me where it is, it'll save me a little time.
What section?
And therefore, this is in the chapter 8, right after priest, I believe. Or maybe actually it might be before, somewhere in there.
It's 483.
Okay, page 483. All right, now that means you calculate VOC equal to the square root of 4 times R rad, that's the radiation resistance of the antenna, it has nothing to do with the load, times P received. And P received is the theoretical max. Just note that. This is important right here. All right, and that's a peak voltage. Y'all with me? Now, hear me on this one. If that's the case, if that's the open circuit voltage right there, now things make a lot more sense. For instance, how much power is received by that second antenna if there's no load, if current can't flow? Anyone? Zero, right? If no current can flow, you can't have power, can you, class? You need V times I, don't you? Right? There's no current, no power. And now all of a sudden, oh, I didn't think of that. That P received is strictly for theoretical purposes. It's to get the open circuit voltage that will be right inside this thing. So if you had an open circuit and you connected a meter right here, this is the voltage you would read. You all with me? Now, it's not the voltage available to push current out here because there's a source resistance and possibly a reactance in there. So when you do the complete circuit, what you do is this. Over here. I know I've got an antenna, right? And I've got some load. I don't know what my load is, just call it Z load. This is the real one. You say, if I want to find out what, say, either the current is or the voltage across that load, what I do is say that really I'm going to look at the antenna circuit as plus or minus an open circuit voltage here. That's given by that equation. Then I put the source impedance. Now I put Z antenna here, which can have a real and imaginary part. And now here's where I come out of the antenna. And I put my actual load. And now I calculate the current by taking V open circuit dividing by Z antenna and Z load. Because Z load does not have to be the conjugate of the antenna piece. It can be anything. In real world circuitry, rarely do you get it, if you're talking about inexpensive units, do you get this load equal to that antenna piece? You just don't. They don't care. Right? Most of the time, when you have an antenna, this load is really looking for a voltage. It's a very high input impedance. All right, it's like an FET input. So it's basically, a field effect transistor, MOSFET, for instance. It has basically a capacitor at the gate, right? And if you've got that, what you've really got is something with fairly high input impedance, unless you've got an extremely high input frequency. Do you follow me? But that voltage there will modulate the current, so you can get a lot of amplification off an input voltage without drawing much current. It's not like, yeah.
So if you match the antenna with the conjugate using the Z
If this was the conjugate of that, then you'd have maximum power.
and max power, like the voltage across the load is going to be half of
Then the voltage here will be half this voltage. But remember this much, all right? Because these are conjugate, the current will be the same, right? And if these are conjugate, then the voltage here may be V naught at 30 degrees, and this will be V naught at minus 30. You follow me? So you can't just say this voltage plus this voltage without adding the angle equals V open circuit. Be careful of that, I'm warning you. Calculate the current first. Then if you want the voltage here, take that current times that Z. Yeah.
I'm a little confused. What is the difference between Z of antenna and Z of source? Are they the same?
You mean?
Like maybe that's, I was thinking like.
Yeah, the antenna, see, yeah, this is the equivalent source impedance.
Okay.
Right? I mean, because I'm saying this VOC is theoretical open circuit voltage on that antenna based on a maximum possible received power, right?
Mm-hmm.
Now, I put Z antenna there, which is a function of frequency. Now I can hook up anything I want. I can figure out what happens. If the load is an open circuit, then my output is VOC, right? Y'all with me? We just cut this. Then I don't have any current, got no loss through the Z antenna, therefore that is in fact equal to VOC. You all with me?
Does the load impedance function kind of like a source impedance on a transmitting antenna?
No, I mean, this is strictly receiving. All right. Yeah. See, here we're going to get into problems. The transmitting antenna has a separate power source that is driving the actual antenna's impedance, right? Here, we're receiving power. So we have to create some way of doing the math and finding out things. So really, there's actually an open circuit voltage equivalent we can put in there with the antenna impedance in series with it. And then we can attach whatever we darn well please, and that will be the actual voltage. When you do the analysis, we'll get the current or voltage. Now, I'm trying to, what my real point here is, in the real world, the voltage, the impedance here is rarely matched to that, rarely. They just want to they want this thing to draw very little current so they get a voltage there, and that's going to feed an FET front end or a differential amplifier FET, and that will be used to amplify it several times. Typically with antenna circuitry these days, I'm just going to get right to the core. When you receive a signal, you amplify it. You may amplify it through twice, all right? And then, in the real world, they digitally sample at a very high rate of speed. They take those sample values and then they go through and they quantize into 1028 different 2 to the 8, 2 to the 9, 2 to the 10th, different possible values. You all with me on this? And then when they have that, then they do digital signal processing for all the things they're going to do. Either DMOD, I mean, that's the way it's done most of the time, except at very high frequencies. And then you will have intermediate frequencies. You'll have basically, do y'all know what mixers are and stuff? Do you know that term? All right. So you're going to mix a signal with higher frequency signals, and you get basically a sum and difference frequency. Then your low frequency filter the low signal. So they'll do that. That's analog processing sometimes. But more and more these days, everything is digital. After they do that first or second stage of amplification off the antenna, they start sampling at a super fast rate, quantizing, and then taking that signal and doing any processing from there. So digital signal processing basically has no noise in it, and it's very easy to do. Analog stuff, using inductors, capacitors, and circuitry, it's got a lot of inherent noise. I'm just trying to tell you this. If you're looking at old books that talk about how things are done off of an antenna, you're going to find a lot of stuff that ain't done that way no more. And I have to be very familiar with this because I'm teaching EMC and I'm doing stuff and doing radar work, and everything's going, they call it software defined. It's just digital. That's all I mean when they say software-defined radio, software-defined radio. It means there's no mixers. Everything's done with digital signal processing. And by the way, you guys are familiar with some of the microcontroller circuits, right? And, well, or microprocessor. Microprocessor is a lot more money. Well, microcontrollers, my wife works at Archangel, and she gives me blow-by-blow stuff. They have digital signal processing package. These microcontrollers are $10. You can do everything with $10 that you need, and you can modify it at will. So why have all these other circuits that usually cost a lot more money, that require power supplies that are a pain in the butt? And that's why they do digital signal processing. Okay, so that's the full circuit. That's important. How we do radar, one of the things I love. I like teaching EMAG too because stuff that I'm involved in, both research and stuff like this, is the stuff that I'm teaching about. And I'll try to keep you abreast of the most. And if you look in the book, I think this is the next section, radar. So, y'all have heard of radar, right? Radar really has to do with radio, ranging. So, I mean, you can look at the acronyms. but it's really using radio frequency electromagnetic information to find the range from targets using an echo. The analogy to radar is sonar, and it's what bats used. And if you want to know something, you can really kind of make it analogous to, have you ever been like in a canyon or anywhere where you say, you know, you hear yourself after time delay? Well, that's an echo return. Bats use it, dolphins also. All sorts of creatures. I shouldn't say all sorts, a lot of things, a lot of bats, a lot like whales, dolphins, porpoises, they use it. And they just create sounds and they listen for the echoes. And bats are really amazing. I'm telling you, they're absolutely amazing because they can, with 100 bats around it, close, they can see if there's an insect next to them and get in complete darkness. So they can get rid of all the reflections from other bats. They do all sorts of amazing things. Bats are sort of what I'm looking at as my model for how to actually build a very useful radar for like drones and stuff like this. Would be delivering packages. Yeah.
Does that mean each bat has its own frequency that it's working at? Or?
You know, you can tell my voice, right? Can you tell his voice? Matter of fact, if I close my eyes, I could tell the difference without ever tuning my ear, right? Because I've been exposed to it. Every bat is as unique as your voice and mine. And they even shape their voice. So if they want an echo from a certain structure a long way away, they'll use probably a higher, it depends on the environment, either a lower or higher frequency. It has to do with the losses. And they'll put out more energy. Bats are amazing. But when we try to do what a bat does, it doesn't work because their neural nets are insane. I'm going to tell you more about this. A neural net is your brain, basically, all right? They can think much, much better than our best computers can, and they can do it that fast. What would take us a year to do, they can do in a nanosecond, it seems. I mean, they can, that's a little exaggeration, but they can do it instantaneously, virtually. So anyway, back to radar. It's radio and detection ranging. So radar itself came about in World War II. But theoretically, they knew they could do some of this even back in the First World War, but they didn't have any of the interest or technology. So radar came about, modern radar, in World War II. And it's pretty amazing. This is just the first order look at radar. It uses electromagnetic radiation, or it uses antennas. Typically, I'm going to say at about, typical is a gigahertz is typical. All right. I mean, K-band, the old police radars were 10 gigahertz. That was an X-band. Now they're Ka-band down here. That's 33 gigahertz. But they're not up here at 600 gigahertz or something. So these are modest frequencies. You can engineer things around very easily. So with radar in general, here's what happens. You have an antenna. Well, the first thing we worry about is the power received. We're going to have a transmitting antenna, and it has a gain, and it's going to transmit a certain amount of power. Are you with me? So you're assuming this thing has a gain. It's an antenna. It doesn't matter what type. It's transmitting power. It's going to transmit power out to a range R. And then out here, there's going to be a target. So the power is propagating this way. You could say the E field transmit is propagating this way. And it's going to strike this target. We really care about the power density right here. We want to know what the average power density is on that target. But when I talk about a target, we don't care about anything except what's called the radar cross-section. So we talk about the radar cross-section. Units are meters squared, and Typically, it's abbreviated RCS. And this symbol we use is sigma, which I don't like, but I didn't choose it. It's universal. They use sigma for radar cross-section. Anytime you're wondering if that is the radar cross-section, it'll have the units in meters squared. All right, so it's an area. So when I have this P average incident on here, first what is P average incident from that antenna? P average incident right there at the target, I'll just call it P av at the target right here. Well, that's the transmitted power, right? Do it the way I've taught you, over 4 pi r squared. That's the power density as if it was isotropic, right?
Mhm.
Then multiplied by the gain of the transmitter. Now, and you always worry about power density. So that's the power density on target. Now, some of that go ahead.
Can we use a different denoter for target?
RCS, you mean?
Or, well, no, like P transmit and P target, are they different or are they the same?
Well, all right, how about we use P rad?
Yeah, thank you.
It's fair. Back here, I'll call this P rad. I agree with you. Now, that power, right? Yeah, that power density, when it strikes this target, some of it's reflected, right?
Mhm.
Here's how we do it. We find the total power reflected, just call it P reflected. Total power reflected is sigma times the incident power density, right? In other words, whatever the incident power is, multiply that by the cross section. Just look at the units. Power density, watts per meter squared. Target, meter squared. Now we get watts, right? I want to say one other thing. That value of sigma is like the antenna gain. It is a function of angle. And if you think of an aircraft for a moment, think of how an aircraft looks broadside versus coming right at you, right? Just in terms of the picture you'd get in the optical range. Electromagnetically, there's that much difference too. As a matter of fact, the electromagnetic size of a stealth fighter, if you're in the military, in the F-117 coming straight at you, and this is a big jet in my opinion, not big by some standards, coming straight at you is less than a seagull at typical radar frequencies. It's just about invisible. All right, that's why stealth scares everybody that doesn't have it, because you can sneak up and blow them up and they don't even know that somebody snuck up on them. So that's total amount of power reflected. So what I like to do, once you see that, now when I want the power density back here, that would be P, this is going to be the density, so I'll call it P av received. Just follow me on this, and I'll write the whole equation. P av received here. Now I take that power, now watch, I'm going to take sigma. Then I take the incident power density, which is gain of transmitter times transmitted or radiated power, right, over 4 pi r squared. That's the total amount of power reflected. Do y'all see that? That would be the total power reflected, and it's not P av. So I'm going to call this P reflected. Let's do it this way. Make sense to everybody? Power density times the size of the target's power reflected. Now we're going to get the power density back here, P av received. Now I can say that the average power density received would be equal to this all right, but then I divide that by 4 pi r squared. I want you to see what I'm doing. All that power is going to fall off as the surface area of a sphere. Now there is no real gain associated with that target's reflection. It's all wrapped up in sigma. Sigma will be a function of angle. It will be bigger if that stuff's coming right back at the target than it will be if it's hitting and you're looking at 90 degrees. Do y'all follow me on that, class? And then we'll speak more to that in a bit. Now that's the power density back here. What do we know if we have power density? We want to see how much the power of the antenna actually gets from that power density. What do we have to multiply it by? We have to multiply it by the aperture, or lambda squared over 4 pi times the gain. Do y'all remember that? With me on that? You have to have the electrical size, and that's the aperture. Let me put it down here. This antenna looks, the aperture, AE of the antenna, or AP, is equal to lambda squared over 4 pi, right, times the gain of the antenna. We'll assume gain of the transmitter is gain of the receiver. It doesn't have to be. And so now, if I want the power received back at the antenna where the radar is, in other words, the receiver and the transmitter don't have to be the same, but we're going to assume they are. Then I'll do this. I can say that P received here, it's going to be all this. Here, I'm doing it on purpose this way. So it's going to be sigma times G transmitter times P rad, right? Then it's divided by 4 pi r squared squared, right? Because I got 4 pi r squared twice, with me? Then I have to multiply that by the effective aperture of that antenna. And that aperture would be lambda squared over 4 pi, and it would be gain. And I'll put gain of the receiver here, because they too can theoretically be different. So if you divide P received by P radiated, you get a ratio of something. It has nothing to do with the actual powers. And that's the typical thing that's important. It's called the radar range equation. So with radars, if they got a target a certain distance away, and here's the one you get down. They say the amount of power received, this is called the radar range equation. Sometimes it's abbreviated RRE. It's P received over P rad. And that would be, now just take a look at this. You're going to have, down here, you'll have 4 pi cubed r to the 4th. Then you're going to have gain of transmitter, gain of receiver, lambda squared, sigma. And you can see in here, what I've done is divide by P rad, and I've combined things like 4 pi and r squared. Now that's the way it appears 90% of the time. It's the most basic, called the radar range equation. It says it's a ratio of how much power you're going to receive compared to what you send. And it's small. Now take a look how small it gets, how fast it gets small. That's r to the 4th. All right, think rationally now. If you're 100 meters away, 1 over r to the 4th would be 1 over 10 squared to the 4th power, 1 over 10 to the 8th, right? Now go out 1,000 meters. That's 1 over 10 to the 3rd to the 4th power, right? 10 to the 12th. It went from 10 to the 8th to 10 to the 1 over 10 to the 12th, right? Hold it. Did I say that? It's going to fall off. When you're falling off this r to the 4th, here's what it means with range. If you can see something perfectly at 100 meters, no problem, you got it. At 200 meters, you might not see anything because it's falling off so fast. The power you're getting back is 1 over r to the 4th. That's tremendous. When you talk about radars, especially space radars from here to space, when they can see something, a normal size satellite, that's astronomical. You don't know how hard that is because they're sending and listening. It's not just seeing a star that's coming one way. They've got a scent, the information falls off as R squared, 1 over R squared. Hits, then the little bit that's scattered falls off as 1 over R squared. It's a phenomenal amount. Okay, now for your quiz. I figured I'd throw those stories in, it helps. I had professors that would try to tell us stuff that was, in their experience too, that were beneficial. Would you spread out